Okay. Okay, so today we're looking at, the reactions we're looking at are going to be forming epoxides, hydrogenation, and we might get to oxidation states. And then on Friday, there's basically there's 3 more reactions, and I expect we'll do those. And then next week, well, we'll see how far we get both days. But if nothing else, on Monday and Tuesday of next week, we will be talking about regio and stereoselectivity once we have all the reactions down and doing problems next week. And we do have class on Monday, and we do have class on Tuesday. If you don't want to come, that's fine with me. It's not my problem. Could be your problem, but it's not mine. If the university wanted us to have Tuesday off, they would have canceled all classes and we'd start early. But we're having class. And I don't know, there's probably let's say there's 35. I don't even know what I'll put the under-over on. I will record it and put it up in case you're starting your holiday vacation early. But if you come to me and say, it's cool, I'm gone next week, right? No, it's not cool, you're gone next week. So you may have no choice in the matter, but if you start your thing, it's cool, I'm gone next week, yeah, don't do that. Because there's worse emojis I can find to post on Piazza when people ask if we have class next week. I tried to find a tame one, but there's probably other ones out there. So that's what we're doing. Like I said, and if you have questions, you can always post them on Piazza. I will be keeping track of answering questions as much as I can. Okay, any questions to start with on any of our reactions? Because we're gonna basically start with sort of the bromonium ion, or like the bromonium ion today. Well, as I go, if you do have questions, you can raise your hand. If you don't want to do that, you could, I suppose, text them into the Piazza, and I can see whether or not I'll see them in real time. And people are mixing lab and lecture Piazza. That's fine. Just realize Dr. Simmons only has lab Piazza, not lecture Piazza. So I'm the only one seeing the lab Piazzas if you're putting them in there. Maybe that's your intent. Okay, let's start with this. So if I start with this alkene, one of the things I can do is, as to review from last time, we can add Br2 and H2O to this. Okay. And so with the bromine and water, my 3 things that I need to know about that is, what am I adding? What 2 things am I adding? Water, well, not water, but OH and Br. So I'm going to add a Br and an OH. Markovnikov or anti-Markovnikov? It's going to be Markovnikov, but in what sense? In the sense that the Br plus is going to act like the hydrogen, and the OH minus is going to be the nucleophile. Remember, that's not the real mechanism, but the Br plus is going to act like the electrophile, so it's going to add to the carbon. If Br plus is acting like H plus, Br plus is going to add to the carbon with the most hydrogens. Okay, then the OH will add to the other. And so I am adding Markovnikov, a broader definition, and then 100% cis, 100% trans, 50-50. 100% trans because it has a triangular intermediate. And when we're all done with our reactions, we'll develop a table, but you could be developing your own at this point.
How do you determine if it's Markovnikov or antimarkovnikov?
So in this case, because the bromine is acting as the Br+, it's going to add to the carbon that has the most hydrogens, because then that's going to leave the other carbon. In this case, in the triangle, it gave it more delta positive charge, and that's where the water was going to add. So and this is true for the mercury. The mercury is mercury plus, so it's going to add like H plus, so it's going to also be Markovnikov addition. So our broader definition of Markovnikov is you add E plus to the carbon with the most hydrogens, then the nucleophile to the other carbon. That's our broadest definition of Markovnikov. Okay. So if I said, what's the product of this reaction then? We would say that we've added the bromine to the carbon with the most hydrogens, and we've added an OH to the other carbon. And in this case, because it's not cyclic, it's going to add 100% trans, but we'll see that there's really no way to draw that exactly in this molecule. So there's my product. Okay. Now, this is called a Bromo Hydron. And the question is, what is the purpose of a Bromo Hydron? Well, Bromo Hydrons can undergo one reaction. And that is that if I take that Bromo Hydron and I react it with base. So if I take that Bromo Hydron and I react it with hydroxide, you might say, well, the hydroxide will come in and do SN2 on the bromine. No. What the hydroxide is going to do is it's going to deprotonate the OH. And when it deprotonates the OH, it's going to form an O-. Okay, so we form an alkoxide. Because the bromine and the OH group that's now an O- group added trans, this O- is in the perfect position to now do a backside attack on that carbon and kick off the bromine. So this is going to be what's called an intramolecular Sn2. Okay, so this is going to be intramolecular. Which means within the same molecule. And so what happens when the O- comes down, kicks off the bromine, is I form a three-membered ring that has the oxygen in it. And so that three-membered ring is what's called an epoxide. That's the common name. So a three-membered ring with an oxygen is an epoxide. IUPAC, it's called an oxirane, is its name, but we'll call it an epoxide. So epoxides are good intermediates that we can use to do other reactions with. And so this is method one to make an epoxide, is to take our Bromo Hydron, deprotonate it, and have it do an intramolecular Sn2. Okay. So that's what we do with Bromo Hydrons. What we do with epoxides, we'll talk about in a minute. Okay. All right, so everybody kind of okay with that? And this wouldn't work unless the OH and the Br were already trans to each other. In this acyclic system, it can freely rotate, but in a ring system, they'd have to be trans, which they are. Okay. So another way, and probably the most straightforward way of making the epoxide, is to take the double bond and react it with what's called a peroxy acid. So this is a peroxy acid. A peroxy acid is a carboxylic acid, C double bond O, OH, with an extra O in there. And that extra O then is going to basically be plopped down on top of the double bond to form the epoxide in one step. Okay, so this in one step, I'm going to form the same epoxide that I just did with the O and the CH2. So this is a one-step method to make an epoxide. Okay, there are some stereochemical consequences of that. And so if you can imagine that maybe I have a double bond that would be trans in stereochemistry. So let's say I have my ethyl group and my methyl group here trans. If the O is just simply coming down and sitting on top of the double bond and forming both bonds at the same time, whatever the stereochemistry is here is going to be translated over and preserved in the final product. So when I do this reaction with trans, I'm going to end up with an epoxide that is also trans. So that the ethyl and methyl group are going to be trans in that three-membered ring epoxide. And the two hydrogens are trans. Now, if it just added oxygen to one of the two carbons, there could be free rotation so that I would get both. But in this case, when that oxygen comes down, it forms simultaneously the bond between both carbons at the same time. So if you start with trans, you're going to make trans. If you start with cis, you're going to make cis. And so this reaction we will define later on as a stereospecific reaction. So Friday, Monday, Tuesday of next week, we'll get more into stereoselective, regioselective, which the book kind of incorporates, but we're going to take them all at once. There's also a third term called stereospecific. And so I'll define those terms exactly. Stereospecific is different than stereos and regioselective. Okay. So this epoxidation reaction is stereospecific. And this is the easiest way to make an epoxide, is just to use a peroxy acid. Right. So we can make epoxides two ways. Bromo hydrons treated with base, or alkene directly treated with a peroxy acid. All right, everybody kind of with me? Because then the question is, what do we do with epoxides? And what we do with epoxides is we open them up. So we take this epoxide that I just made, and if I'm going to open them up right now, the first thing I need to do is I need to add H plus to them. So in this case, what I'm going to do is I'm going to add H plus and methanol to this epoxide. And this is going to be called acid. It's going to be called acid catalyzed, even though that's not a particularly great term. It's going to be called acid catalyzed ring opening. So what I'm going to do is I'm going to open up the ring in this reaction. Right. So the first step in the mechanism is I'm adding acid to an oxygen species. So the first step is going to be protonate the oxygen. Right? Protonate the oxygen. Right? I'm going to say that over and over and over again. Oxygen plus acid, protonate the oxygen is the first step always. Okay. So what's that going to do? It's going to protonate the oxygen. It's going to turn that oxygen into an oxonium ion. Is that oxygen happy? I mean, it can live with the positive charge, but what I would really like to do is to dump that positive charge off on something else. What's the something else? How about those two carbons? So we can think of this epoxide looking like this protonated epoxide. We could think of it kind of looking like this. It's going to dump the positive charge down onto carbons A and B. Anybody having a sense of deja vu? Which is French for what? Been there, done that. At least it's not Latin. At least it's not quid pro quo, that no one knows what the meaning of that is. Oh my God. What's that look like? Where have I seen that structure before? When I added the first bromine, right? That looks like a bromonium ion with the bridge. It also looks like what else bridged? From last Friday, the mercury. So the mercury and the bromine formed a triangular bridge. So does this epoxide basically once you protonate it. Right? Doing the same thing I did on Wednesday. And I'm going to even go a little bit further and say, you are methanol. What kind of nucleophile are you? Strong or weak? Weak. Who are you going, and I got to make sure that we're all on the same page here. Who are you going to add to? Who is the methanol going to add to? Carbon A or carbon B? And I think we're going to vote on that. So where is the methanol going to add? Carbon A or carbon B? There's no C for both. You've got to choose one or the other. Okay, so which one are we adding to, A or B? All right, we have 22 to 8. We've got 22 A's and 8 B's. Why is the methanol going to want to add to A? Okay?
So if the OH moves either to the left or the right, you want it to move to the right so that you're making a secondary carbocation instead of a primary.
Okay?
And then that way, whichever one the OH does go to, that's the one to the methanol.
Does that make sense to everybody? So trying to figure out which one of these two would be the true carbocation if the mechanism went that way. And so it would more likely go to A because A would form a pure secondary carbocation. Except what did we say on Monday? The only slight modification to that answer would be we don't ever form the true carbocation, because we still have to maintain the bridge, because I guess what I didn't tell you is that the methanol has to end up trans, 100% trans to the OH when it's done. But then again, I don't know that I needed to tell you that, because every time we have a triangular intermediate, it will always be 100% trans. So in this case, the methanol is going to end up 100% trans to the OH. Because this carbon looks like a secondary carbocation in quotes. This carbon over here looks like a primary carbocation in quotes. On Monday we said that we were doing water then, but water, alcohol, it's all the same. That the water added to the carbon with the most delta positive charge, which in this case is the one that is most substituted. Okay. So what we're going to find is anytime we open up an epoxide with acid, the nucleophile is always going to add to the most substituted carbon in the epoxide. Why? Because that's the carbon with the greatest delta positive charge. So our major product, the methanol, adds here. That causes the OH to slide over to be bonded to the primary carbon. So I'm going to end up down here with my oxonium ion. Over here with my OH. And then the final step, what happens? I lose my H+, which is why this is acid catalyzed, because I used acid at the beginning and I'm generating it at the end, so that I end up now adding the OCH3 group and having the OH group. And if I did this with water, I would end up with two OH groups. So the reason I'm showing you this mechanism with methanol is because now you can go back to Monday and last Friday, because I could have used mercury with alcohol and added an H and an OR. I could have reacted bromine with alcohol to make a bromine and an OR. So anything you can do with water, you can do with alcohol. It's virtually the same mechanism. So this is how we open up an epoxide with acid. Now, this is not Markovnikov or anti-Markovnikov. Markovnikov and anti-Markovnikov only mean something when you're adding groups to double bonds. So when I'm doing a reaction of an epoxide, it's not Markovnikov or anti-Markovnikov, because those terms only refer to double bond reactions. When I make the epoxide itself, it is not Markovnikov or anti-Markovnikov. Okay, is everybody kind of with me here? So where we see the stereochemistry show up is in the double bond, is in the epoxide. So let's say I had a CH3. Let's say I had this molecule with the double bond. And I said, I want to react that with my peroxy acid and make the epoxide. You could show the epoxide as either two bold wedges or two dashed wedges. I switch back and forth between that, but I'm just showing you wedges to show that the oxygen is bonded to both carbons above, in this case, above the plane of the ring. When I add my H+, I'm just simply going to protonate it. And that positive charge is going to feed down to those two carbons. Then if I was to add water, where would the water go? The water would technically add to the carbon that's most substituted. So it would come over here and add there. The critical part is that if the epoxide oxygen is above the plane of the ring, then the O8, the oxonium ion, would have to be below the plane of the ring. And over here, the OH, when it slides over, would become above the plane of the ring. And then there would be a CH3 here. Then minus H+. And my final product then would have the two OH groups, trans. It doesn't really matter if they're on a bold or dashed or bold. As long as they have opposite wedges, they're trans, and that's what's important. Okay. So this would be an epoxide plus H plus H2O. So what epoxides let us do is epoxides let us basically create new molecules by opening them up, by opening the molecule up. And so what kinds of reactions can I do with an epoxide? I can add H plus H2O. I could add H plus, and let me just make a generic alcohol. I could react it with an alcohol. Or I could even add H plus, Br minus, Cl minus, etc. So I could use HCl and HBr. But these reagents, this is what I can add to an epoxide. In each case, the nucleophile will add to the carbon that's most substituted. And the OH will end up sliding over to the other carbon. Okay, does that make sense? So those ring openings have to come from the epoxide, which you can get simply by reacting the alkene with peroxy acid.
Can you explain real quick the role of that molecule at the top for RCOH?
So what this does is what one of these oxygens ends up coming over and inserting itself to form the epoxide. So one of those two oxygens is the oxygen that's in the epoxide. So the way I can draw that, and this isn't the real mechanism, but it'll work for trying to figure out what's going where. If you have a carbon in your double bond and you have your oxygen here of the peroxy acid, you could imagine something like this, where this pair of electrons goes to form the CO bond, and then this pair of electrons comes down, and then somehow this OH ends up over attached to that carbon. So what we do is we're adding this oxygen to both carbons simultaneously, so that in the end we end up with our epoxide. So that's what the peroxy acid does. It adds an oxygen to the carbon-carbon double bond. But whatever the carbon-carbon double bond stereochemistry was, cis or trans, the epoxide ends up cis or trans. The stereochemistry is conserved. So that's what we can do with epoxides. Make them and react them. The characteristics of epoxides reacting with acid are very similar to the triangle of a bromonium ion and a mercurium ion. And that's why it's in this section of the book, because we're just dealing with all three of these things at the same time. Okay, everybody okay with that? All right. The other reaction that's in the sections for today is what is called hydrogenation. And in hydrogenation, what I'm going to do is I'm going to take a double bond. I'm going to take a double bond with two methyl groups. And I'm going to add hydrogen gas to it. And in order to add hydrogen gas, I need a catalyst, which in this case is palladium or platinum metal. So this requires a metal catalyst. Now what we should do is we should take a little step back. And this is hydrogenation, which is a type of reduction. Now, what is oxidation and reduction in the context of organic chemistry? In general chemistry, reduction is what? Loss of electrons and oxidation is the gain of electrons. I don't use oil rig as my mnemonic. I use Leo the lion goes grr. That's the one I use. I'm not even quite sure what the oil rig stands for, other than there's an O for oxidation and a R for reduction. Although I can see the reduction, I can't. That's why I use Leo. Problem in organic chemistry is, in order for us to keep track of electrons, we would have to assign oxidation numbers to carbons, which, by the way, for the reading today was the middle section, how to assign oxidation numbers to carbon, which I'll come back to. Because the easiest way for us to look at oxidation and reduction is, reduction means that in general you've gained hydrogen or you've lost oxygen. Whereas oxidation means that you've gained oxygen or lost hydrogens in the molecule. So using the oxidation and oxygen and hydrogen ideas, it's easier to tell whether you're undergoing reduction or oxidation. In general chemistry, it's like, oh, I'm going from Fe3 plus to Fe2 plus. Oh, that's a piece of cake. But if I'm going from this molecule with a double bond to this molecule that'll have two hydrogens attached to it and no double bond, it's a little more difficult to understand where the electrons and how the oxidation numbers are changing. It's not terribly difficult, it's just adding and losing oxygens or hydrogens is easier. So in this case, it's a reduction because I'm gaining hydrogens. In lab, what did we do with the yeasts? We took our ketone and we converted it to our chiral center with the OH. So what did we do? We gained hydrogens, so that was a reduction reaction of the carbonyl. Right. But we'll come back to oxidation numbers of carbons. Like I said, if we don't get to it today, we'll get to it on Friday. So this is hydrogenation. For hydrogenation, what am I adding? I'm adding 2 hydrogens. Markovnikov or anti-Markovnikov? Neither, because I'm adding the same thing. So it's neither Markovnikov or anti-Markovnikov. What about stereochemistry? It turns out that stereochemistry is 100% cis. And so when you react this 1,2-dimethylcyclohexene with hydrogen, you will get the cis dimethylcyclohexane, 100%. As long as they're on the same bond. So in this case, they're both dashed. If they were both bold, that would be okay as well.
Do we need to know why that's the case, or is that more of just like a memorization type of thing?
Well, I'm not going to ask you to do the mechanism, but let me show you what the mechanism is. Because we can relate the mechanism back to, I forget. I know I'm not the only one. We've already had another reaction that added cis. That added 2 groups cis. What reaction was that? Who said it? Say it loud. Hydroboration oxidation. Added an H and an OH, 100% cis. I could say remember, which you eventually will when you get to that in your notes, in the pages of your notes. But we added a boron and the hydrogen to the double bond in a square, right? And that was cis. So the same thing is true here, although the mechanism is far more complicated than this. If I have my palladium or my platinum metal surface, what happens is that the hydrogen gas adsorbs onto the surface of the palladium. And then what happens is that then your carbon-carbon double bond comes down and it approaches the hydrogen that's adsorbed onto the surface. Well, we know from the mechanism that both hydrogens have to add at the same time. So you can think about the mechanism looking like this. Maybe I take the pair of electrons, move like this, take that pair of electrons in the HH bond and move it like that. So that what we would have is something that we've seen before, we have a square transition state. Okay. So the reaction occurs as the alkene is at the surface of the palladium platinum metal. And the mechanism of this is probably much more complicated than that, simply because you've got a metal surface in probably the gas phase, or at least liquid where this is happening, some sort of liquid-solid gas interface. This reaction is extremely important because there's a lot of palladium platinum metal catalysts that are used in the refining industry to take long chains of alkanes that we get from crude oil and we chop them up to make smaller ones that we can fit in our gas tank. They all fit. It's just that some of them, like 30 carbon chains, are better left to put on the road as asphalt as opposed to put in our gasoline or in our tank to burn. So there's a lot of those metal catalyst reactions that are used, and they're not necessarily always understood. Because there's things that can get on the metal to poison the catalyst that'll, kill very, very expensive catalysts in a refinery situation. So this is simplified why that happens. So it's not just that it adds cis, it's that it adds cis because of this. So all these reactions that I've given you where I said you aren't responsible for this reaction, I've still shown it to you, not because I like to, talk. It's because that way if you go, how does it add? Then maybe you can go, okay, it's a surface, all right, that's the square cis. So that you have something to relate it to. Okay. And then there are a certain fraction of students that don't like to learn unless it has a relevance. So the metal surface is used in refineries. That's your relevance if you're one of those people. And I'll show you another one that's relevant as well. So that's how it adds cis. So this is hydrogenation. And this does happen to take alkenes and reduce them down to alkanes, which burn a little bit better than alkenes. If we go out and we grab a sample of crude oil from someplace, it's going to have alkanes, alkenes, and alkynes in it. And probably more alkanes than alkenes and alkynes, but we have to somehow, in the refinery, they've got to get rid of that. And they've got to chop it down to very specific chain lengths so that we have gasoline versus kerosene versus fuel oil versus stuff that goes on the road, which is asphalt. So the refinery produces all these different products. And crude oil is still what we use. We don't have enough solar panels and enough nuclear. Oh God, we don't have any nuclear. Can't have nuclear, so we need, wind. Not enough wind right now. Sun's only around half the day. So we still have to use crude oil, if nothing else, to make these materials that we're making our solar panels and our windmills out of. So maybe the day will come when we don't need to worry about crude oil anymore, but we still do. And crude oil we're only 2 hours away from where crude oil was developed in western Pennsylvania. And I know the little town I'm from there at one point had 17% of the refineries in the world in the early days of refining before John Rockefeller came and took them all over. Or they caught on fire, or they just something. The oil business was a rough business to be in back in the 1800s. It was a rough and tumble business. One whole town, Oil City. If you're from western Pennsylvania, you know where Oil City, Meadville, Titusville's where the Drake's Well is. But the lightning hit a tank during a thunderstorm where the river was overflowing, and all of a sudden it hit the tank. The tank washed all this water into the thing. Then the lightning hit it, and it was like a ball of fire moving down the river, and it was just a horrible thing. A lot of people lost their lives. Their fortunes went sometimes to places like in the county where I'm at. There's a whole place that's named after somebody who died in one of those tank explosions. So it was a rough business to be in back in the 1800s, but it's still what we use. A little bit safer, maybe. So crude oil is still important. The example I'm going to show you is not crude oil. It's fats and oils. So here's a practical example of hydrogenation. Let's say that you take and you have a molecule that looks like this. long chains of carbon atoms. Sometimes the long chain of carbon atom will have a double bond in it. Sometimes it'll have multiple double bonds in it. Sometimes it'll have no double bonds in it, and it'll just be an alkane. So, does anybody know what that is that I just drew from biology? It's a triglyceride. If it had a phosphate group over here, it would be a triphosphocholine or whatever it is. So this is a triglyceride. And a triglyceride is the common name for a fat or an oil, depending on what the physical species of the fat or oil is. Fats are solids, oils are liquids, and that's how they're defined. So if you go to the grocery store and you want some fat, you got to get something that's solid. Coconut oil, lard. Lard's a fat. People cook with it. When I lived down in Athens, there was a Big Bear grocery store, and it had a lard section at the end of the aisle. Every conceivable type of lard you wanted was there. There's really only one lard. It comes from swine. So fats are solids. Coconut oil, the health on coconut oil goes back and forth. One day it'll kill you, the next day it's the greatest thing ever. Oils, you can go get some vegetable oil, canola oil. You can get those. You can make soaps out of both of these, which we'll talk about next semester. But fats, solids, oils, liquid, which are which? When you have what is called a saturated fat, because it has nothing but carbon-carbon single bonds, and therefore has the maximum number of hydrogens per carbon, it's saturated. Saturated fats are solids because the straight chain of the alkane groups allow them to pack together nicely and form solids. When you put a double bond in there, it kinks the system up, and so these are unsaturated because I've now got double bonds in them. Unsaturated oils are liquids simply because they don't pack as nicely because the double bond is kinking up the chain. Okay. So if you go to the grocery store and you're going to make some holiday cookies, then you might be wanting to get some Crisco. Well, Crisco is not natural. Crisco is made by taking the vegetable oil and hydrogenating it to form the saturated fat, which is the solid. And that gets us to what happens if you don't hydrogenate all of the double bonds. Then you end up with partially hydrogenated fats, which I don't believe are touted as being good for you. Or you can end up with the saturated fats that are trans fatty acids. I think those are probably bad or something. But if you hydrogenate, you're going to end up with either a straight chain or, I guess, worst case scenario, end up with a cis fatty acid. And I don't know that anybody's ever said anything bad about cis fatty acids. So that's where the term, hydrogenated comes into play, partially hydrogenated. But all of the Crisco type products, which used to be back in the 60s called oleo, because if you get really old cookbooks, like I have my grandmother's Swedish cookbooks, and it says, oh, make it with oleo. And I'm like, what is oleo? And oleo turns out to be Crisco. So that's been around. Hydrogenating unsaturated oils has been around for a long time. So that's where you see these kinds of reactions, in addition to turning alkenes into alkanes in sort of the refining business. Okay. But the critical part is two H's not Markovnikov, anti-Markovnikov, 100% cis. Why? Because the reaction occurs at the metal surface, so it forms like a square. So on Friday, what we will do is we will finish up our reactions, talk about oxidation numbers, and then that'll set up next week to go over in a lot of detail stereo and regioselectivity. So if you're doing problems in the books, which you should, you can ignore the stereo regioselectivity for the moment. If you have questions, ask by things. I've got your assignments here if you would like to get them. And if you have questions, just go ahead and ask on Piazza.